In this lesson, we will define buffer and identify the components of a buffer solution. The purpose of a buffer solution is to resist changes in pH. Buffers can be composed of two different combinations of substances: a weak acid and its conjugate base, or a weak base and its conjugate acid. Conjugate acids and bases are going to be present as salts, and a salt is just an ionic compound, which is composed of a cation and an anion. Let's review some examples of these two different types of ions. We can form metal cations from elements on the left side of the periodic table, such as Na plus or Mg2+, or we can have a polyatomic ion that's a cation, such as NH4+. For the anion, we can have a nonmetal that forms an ion, such as Cl- or S2-, or we can have a polyatomic anion, such as NO3- or SO4-2-. We've already talked about conjugate acids and bases when we talked about the Bronsted-Lowry acid-base theory. Let's look at a few examples to determine the conjugate base for some weak acids. For HF, we will have F-. We lost a hydrogen and our charge decreased by 1. HCN has the conjugate of Cn-. HNO2 is NO2-. H3PO4 is H2PO4-, noting that we only decrease the number of hydrogens by 1. NaH2PO4 has the conjugate of NaHPO4-, or we can write it as HPO4-2- by removing the sodium counterion. When we're actually preparing the buffer, we actually need to find a salt of our conjugate, because I can't go to the stockroom and find a bottle of fluoride ions by themselves. I need to find a compound that contains fluoride ions. For example, NaF is an ionic compound that contains the fluoride ion. KH2PO4 contains the H2PO4- ion. For NaHPO4, we can have Na2HPO4. Some more examples are shown here. Note that the counterion or the metal cation can vary greatly. Typically, we'll use compounds that are formed from the sodium or potassium salts simply because these are always soluble in water, so it makes preparing the buffer easier. Likewise, we can look at bases and their conjugate acids. Here are some examples of some weak bases. The conjugate acid of NH3 will be NH4+. We gained a hydrogen and increased our charge by 1. We can have CH3,3NH+, and we see other examples here for the conjugate acids of weak bases. As with our conjugate bases of our weak acids, we cannot find a bottle of ammonium plus or CH3NH3+ on the shelf, so we need to find a salt that contains that ion. For example, for NH4+, we could get NH4Cl, or we could use CH3,3NHF. Again, the compounds formed with halides are often used because they are very soluble in water. Notice that there are many salts that can fulfill the need to deliver the conjugate acid or the conjugate base. The important thing is that the salt contains the conjugate acid that we need. Which pair can function as a buffer? Remember that a buffer must contain a weak acid and its conjugate base, or a weak base and its conjugate acid. For A, HCl is a strong acid. While NaCl is the salt of its conjugate, this cannot function as a buffer because it has a strong acid instead of a weak acid. HBr and KOH are a strong acid and a strong base, respectively, so they cannot function as a buffer. HNO2 is a weak acid, but it's not present with its conjugate base, but rather present in water. Therefore, this cannot be a buffer. HCN is a weak acid. Its conjugate base will be Cn minus, and we see that KCN contains the Cn minus ion. Therefore, we have the salt of a conjugate base of HCN, making this a reasonable combination to prepare a buffer. HF is a weak acid, and NH3 is a weak base, but they are not conjugates of one another, so they cannot function as a buffer. H2PO4 is a weak acid, and K2PO4 is a salt. However, they are not conjugates of one another. They differ by two H plus ions, and a conjugate acid-base pair but must differ by only one H plus. If we wanted to figure out the conjugate of H2PO4, we would need a salt that contains HPO4 minus, such as KHPO4, which could serve as the conjugate base of H2PO4. Our correct answer, therefore, is D.